In the previous section that we talked about in terms of trying to maximize a function as it's being constrained by another function, um, it's possible that you can get at that same argument by using a certain number that Lagrange introduced when he was solving for a particular phenomenon. And notice that you can also find the extrema by comparing the two equations and then in some kind of way relating one equation within the other and solving it based on some particular parameter that he called a multiplier. And so the goal here is to maximize or minimize a function relative to the condition of another function. You may have a constraint. You may say that what's the maximum temperature, and that was one problem that I don't have today. I wanted to give that to you. I do have another good question for you that I'll raise at the end of all this. But there's one issue. What is the maximum temperature on a sphere? This question was used basically for the Earth. What's the maximum temperature along the Earth's surface as the temperature that you're investigating is confined to a particular region? So in other words, what's the temperature, let's say, over North America or over a particular sector of the country or South America or wherever it may be? And then can you find the temperature throughout the sphere? And then can you calculate the average temperature based on certain conditions? And so the problem gives a condition, and then can you find the average temperature? The idea there would be to apply Lagrange multipliers. Sometimes you can apply this, sometimes it may be easier to apply a different method. My choice methods are a combination of algebra and just calculus 1. But based on certain problems and how they're given, it may be easier to use the so-called Lagrange multiplier. Consider a classic model. Maximize a rectangle within a given fixed ellipse. In other words, let me scroll down so you can see it. In other words, if the ellipse is fixed and we don't know the dimensions of the rectangle, we do know the coordinates of the ellipse is given by this equation, x squared over 9 plus y squared over 16 is equal to 1. Can you find a rectangle and that is inscribed within this ellipse? And then when you find that rectangle, is that the greatest rectangle? In other words, maximize the rectangle within the ellipse. This problem is given in several different ways. You can reverse it. You can take the rectangle and say, what's the greatest ellipse that can be inscribed within the rectangle? Or you could take an equilateral triangle and a circle, and so what's the greatest equilateral triangle that can be inscribed within a circle? Or you can take the equilateral triangle and say it is now circumscribed where the circle is within the equilateral triangle. Can you find the maximum area for the circle given the dimensions for the equilateral triangle? So there's several ways we can get at that. Here's just one, and it's very classic. So what you do to build that is you think about this diagram on the XY plane, and so the dimensions for the rectangle that you want to build you say that if you look at the origin, and if you go from the origin to an edge on the rectangle, we say that we move x units. And then since here this mid-range is said to be the bisector, then we also move from the origin to the left side of the rectangle, also x movements. So here, this so-called, we call that a width, would be 2x. Yes, sir.
Which one of those would be the constraint equation?
The constraint equation would be the so-called circle. Yes, sir. Or the ellipse. And we want to maximize the rectangle. So here the rectangle is being constrained by the ellipse. If you enlarge the ellipse, obviously you have to enlarge the rectangle. If the ellipse is smaller, then you get a smaller rectangle. So here, we're trying to build this function f of xy equal to 4xy. So if you move across 2x, then you also move up and down 2y. And so here we have, in other words, the 2x times the 2y, and that gives you an area. But then you have to solve for the x and the y as it's being constrained by x squared over 9 plus y squared over 16 is equal to 1. I won't go into detail to solving it because it's already in the book. It's one of his examples that he solves, and you can just look at that. That's no fun. I think it's better when we got to do it ourselves, right? So, but that's somewhat the idea of what originated the so-called Lagrange multipliers. Is there a go-between number between this equation 4xy and the x squared over 9 plus y squared over 16 equal 1? Is there a go-between number that's always constant? Lagrange said it is. We call it a Lagrange multiplier. We call it lambda. Here's the method. His theorem says that let f and g have continuous first partial derivatives such that f achieves an extrema at some point x naught, some fixed point x naught, y naught, on a smooth constraint curve. The word smooth here means that the partial derivatives exist. Also, they exist at the endpoints. And so we say that we have a smooth curve, if you will. This smooth curve means to us that there are no jumps in the graph, there are no breaks, and there are no spikes. So this word smooth in mathematics is defined as such. A very neat phrase for that is that all the partial derivatives exist, not simultaneously zero at the endpoints. So here we have an extrema at some point x naught, y naught on a smooth constraint curve. And then this smooth constraint curve is this g of xy equal to c. This would be the x squared over 9 plus the y squared over 16 equal to 1. This guy would act like that, this function g. Here, if the gradient of g at the point under investigation is not 0, then there exists some real number, lambda, such that it's a go-between, that the gradient of f evaluated at the point is equal to some lambda times here the gradient of g evaluated at the point. Now, if you think about it, what he's actually arguing is this, is that the two gradients are parallel. And if they're parallel, they differ by a scalar multiple. The scalar multiple is this lambda Lagrange multiplier. That's basically all he's saying. Okay. Here's the method to solving. It's very easy. Sir? It is. His problems are easy. At the end, I give you some better problems to do in class as a group, and then we'll have some fun with those. So let f and g satisfy the hypothesis above. that the partial derivatives exist. And let f have a minimum or maximum, we don't know, we need to find out, subject to the constraint that g is equal to c. To find the minimum of maximum of f, we use these steps, very, very straightforward. You're going to find the partial derivative of f with respect to x, set that equal to the partial derivative of g with respect to x times lambda. We're going to solve for lambda. Likewise, set the partial derivative of f with respect to y equal to the partial derivative of g with respect to y times some lambda. And then from these first two, you want to be able to somehow solve for g of x, y equal to c with respect to lambda. And I'll show you that. Number two, which most of his problems, he will either tell you that you're looking for a maximum or you're looking for a minimum, but if he doesn't, then evaluate f at each solution point obtained in the first step. The greatest value yields the maximum of f subject to the constraint g, and then the least value yields the minimum of f subject to the constraint equation g. Again, most of his problems are, I call them rigged, so he will say maximize f given this constraint. So he's kind of telling you that you're looking for a maximum. Or he will say minimize f subject to this constraint. He's kind of telling you you're going to find a minimum. So basically, you're only going to find 1 point. If the equations are a little bit bigger, just a lot of stuff going on, then more than likely you'll get several points based on what he's saying here for step 1 and step 2. And then you have to decide when you evaluate here f at the points x naught, y naught. You may have an x naught, y naught. You may have an x sub 1, y sub 1, x sub 2, y sub 2. We won't here, but in numerical analysis, numerical methods course, you get several of those points that you have to kind of play around and plug in to see which is the greatest, which is the maximum. And it's very straight. It's algebra. So let's see. Here's the first problem. Oh, look at this before I give you the first problem. This is a pretty cool idea of what we're trying to do. Find the minimum value of f subject to the constraint. So here we have an ellipsoid, and the constraint is a plane. So he says here, find the minimum value. So what he's actually saying is, find the minimum value of this ellipsoid as it intersects with the plane. So I'm not concerned about anywhere else on the ellipse other than where the ellipse intersects with this plane. So there, find its minimum. Right? And so using Lagrange multiplier, we get that point to be 3 comma negative 9 comma negative 4. Let's see how that works out. Let's do a problem very similar. So here, use Lagrange multiplier to find the indicated extrema. Assume x and y are positive. So here, they tell us to minimize. So we're going to just use those steps. So we're going to find the partial of f with respect to x. That's 2x. The partial of f with respect to y. That's 2y. And then for the equation g, this is what it's being represented as, g of xy is equal to c. The partial of g with respect to x is 1. The partial of g with respect to y is 2. So the method said to take the partial of f with respect to x and set that equal to lambda times the partial of g with respect to x. And then secondly, the partial of f with respect to y is equal to lambda times the partial of g with respect to y. All right, so we do that. We have 2x is equal to lambda times 1, and then and 2y is equal to 2 times lambda. So we have for g, x plus 2y is equal to 5. So I have that relationship. So from the first, I get x is equal to lambda over 2 and then from this one I have y is equal to lambda. So with that being said, I can take x plus 2y, replace the x with its representation of lambda over 2, and then replace the y with lambda. So we have this x plus 2y equal to 5. And so we say, that is to say, lambda over 2 plus 2 times lambda is equal to 5. Now we just solve for lambda, then that gives us the value for x and the value for y. So let's multiply everything by a 2. So we have lambda plus 4 lambda is equal to 10. 5 lambda is equal to 10. Lambda is equal to 2. If lambda is equal to 2, that means that x is equal to 2 divided by 2. So x is equal to 2 divided by 2. We get 1. And y is equal to 2. Now for the function f of 1 comma 2, it's 1 squared plus 2 squared, we get 5. And so again, the problem is rigged. It told you you're looking for a minimum. You only have one point to pick, to choose. That is the point 1 comma 2 comma 5. So we have a minimum here at the point 1 comma 2 comma 5. This is the minimum on f subject to g. Okay. Again.
That's the smallest area.
Pardon me?
That's the smallest area visible in the right.
Now here we're not talking about an area. That was that previous problem with the ellipse and the rectangle. That problem asks for the maximum area of the rectangle subject to that ellipse. This is a little bit different. So here we have a curve, basically a paraboloid, and then they say from that paraboloid, can you find its minimum with the intersection of a plane, right? G is a plane, right? And this F is a paraboloid. And so they're saying on that paraboloid, because that paraboloid itself, it may have its own minimum without G. But then what's its minimum subject to the constraint equation G? So where G and F intersect, can you find the minimum of F? That's all they're saying here for this particular problem. Okay. So there's nothing to it. Yes, sir. I'm sorry. Yes, sir. Want me to go back? I'm sorry. Where are you? Because y is equal to lambda right here. Y is equal to lambda. Yes, sir. And so whatever lambda came out to be, that's y. Yes, sir. Yep. Okay. Everybody good? Try your hand at this one. sound about right? Nobody's saying anything. So it could be either you're still working or you didn't get that, or that could mean that you may be right and I could be wrong, or I could be wrong and I could be right or you could be wrong, or let's see. So when you get right to it, you get 2x is equal to negative 2x times lambda, and negative 2y is equal to 2 times lambda. Did you get that? Okay, very good. So notice that for that so-called constraint equation, that's 2y is equal to x squared. Right. Now, from this equation here, if you divide out the 2x, you have lambda is equal to negative 1. Yes.
I thought that the x squared and the infinite maximized with the 2x was equal to a negative 1 that would go along with the x in the constraint.
Take the partial derivative of the constraint with respect to x, you get negative 2x.
Let's take the derivative of both equations and
You look at the gradient of f, which is 2xi minus 2yj, and the gradient of g, which is negative 2xi plus 2j. And then you set those partials equal times a lambda on the g, right? So it's 2x is equal to negative 2x times lambda. And then negative 2y is equal to 2 times lambda. Okay? All right. So here we have this relation that I have in bracket in a box, and then we have this relationship here. From this relationship, you get y is equal to negative lambda, and then from this relationship, we have negative 1 is equal to lambda. Right? So if negative 1 is equal to lambda, so I have lambda is equal to negative 1, and we get y is equal to negative lambda, that means that y is equal to 1. This implies that y is equal to negative times negative 1, y is equal to 1. Now, if y is equal to 1, and I have 2y is equal to x squared, right? So doesn't this imply that 2 times 1 is equal to x squared, and that implies that x is equal to the square root of 2? So then the function f evaluated at the square root of 2 comma 1 is equal to the square root of 2 to be squared minus 1 to be squared, and I get 1. So I have a max at the square root of 2 comma 1 for y, and then comma 1 for the function value. Yes, sir. Yes, sir. Yes, sir. Yep. 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 That constraint equation, that's the equation that you want to try to put everything into, because if you look at it, it has something on both sides of the equation. You got x's and y's, but it's equal to maybe a number. So you can take that to actually solve. And then whatever the values you get from that, you plug that information in back into that f equation to actually find the maximum or the minimum. Okay? Yep. All right. See if you can get this one. What you get? Anyone? Nobody wants to say. Is that what that means? We don't have anything? Oh, man. Let's see, guys. So you took the partial of f with respect to x, and that gave you 3. Partial of f with respect to y, we got 1. Partial of g with respect to x, you get 2xy. And the partial of g with respect to y, you get x squared. So when we set the partial of f with respect to x equal to lambda times the partial of g with respect to x, so here we get 3 is equal to 2xy times lambda, and then the partial of f with respect to y is equal to lambda times the partial of g with respect to y. You get 1 is equal to x squared times lambda. Now, from this implies that x squared is equal to 1 over lambda. And then y is equal to 3 over 2 times x times lambda. I got that from here. Now I have x squared equal to 1 over lambda. Here's what I'm looking at. I'm looking at this constraint equation. X squared times y. I can write the x squared as 1 over lambda. The y I want to be able to write as a function of lambda alone, but the y here is equal to 3 over 2 times an x times lambda. Well, no problem. X is equal to 1 over the square root of lambda, right? From there. So if that's the case, then we have y is equal to 3 over 2 times x. X, that's a lambda. I didn't mean to put a y there. So this is times x, or 1 over the square root of lambda, and then this is times lambda. So let's simplify that, and then we're going to put whatever we get here for y, we'll plug that into the constraint equation, and then we know that x squared is equal to 1 over y. It's right here, it's a lambda. The left side to the very bottom. This is a y. Yes, sir. This is what y is equal to, and then x squared is 1 over lambda. So the constraint said that x squared times y is equal to 6. So the x squared, we got that to be 1 over lambda. Then times y, this is 3 over 2 times the square root of lambda is equal to 6. So this implies that if I multiply both sides by the lambda times 2 times the square root of lambda, we have 3 is equal to 12 times lambda times the square root of lambda. So I get 1 over 4 is equal to lambda to the 3/2 power. So this implies that lambda is equal to 1 over 4 to the 2/3 power. This is 4 to the negative 1 to the 2/3. So lambda is equal to this is the cube root of 4 to the negative 2nd power. This is the cube root of 1 over 16, or 1 over the cube root of 16. And this is 1 over the cube root of 8 times 2, or 1 over 2 times the cube root of 2. That's lambda. Now I can get x and I can get y. So lambda is 1 over 2 times the cube root of 2. So x, we said, was 1 over the square root of that. X is 1 over the square root of lambda. Y is equal to 3 over 2 times the square root of 3 over 2 times the square root of lambda. 3 over 2 times, take that square root, and we get (16 to the 1/6 power), because that lambda was already lambda was 1 over the cube of 16, 1 over 16 to the 1/3 power. Good. Yeah, it's just the algebra. So that's the minimum. It's a minimum at here, 1 over, let's just write this as 16 to the negative 1 over 6, comma, 3 over 2 times 16 to the 1 over 6. Just leave it at that. I had simplified it a little bit better than that earlier, but that's fine. That'll wake you up, man. Mess you up if you hadn't had any coffee. So, well, let's see if we have one a little bit better. Now this next one, I want you to try your hand at that first. That problem can get complicated as the previous problem, But if you see what's going on, you can work it out and simplify it a whole lot easier. So see what you can do with that one. If it's getting complicated, then you're going too far. You kind of want to look at it, just step back and look at it and see what's happening, and then you should be able to make that connection. Let's see. Hmm? You see it? Yes, sir. All right. I'll give you a few more. So what did you get for the maximum? Yes, sir. So you take that partial of f with respect to x, you get 1/2 6 minus x squared minus y squared to the negative 1/2 times the derivative of the inside with respect to x, negative 2x. So that just gives you negative x over the square root of 6 minus x squared minus y squared. Partial of f with respect to y is similar. Here we have symmetry with f. So this is negative y over the square root of 6 minus x squared minus y squared. Now the partial of g with respect to x is equal to lambda, well, excuse me, is equal to 1. And the partial of g with respect to y is also equal to 1. So when we set the partial of f with respect to x equal to lambda times the partial of g with respect to x, this gives us negative x over the square root of 6 minus x squared minus y squared is equal to lambda. The partial of f with respect to y is equal to lambda times the partial of g with respect to y. That implies that we have negative y all over the square root of 6 minus x squared minus y squared is also equal to lambda. Since they're both equal to lambda, we set both of these terms equal, right? So this implies that I have negative x over the square root of 6 minus x squared minus y squared is equal to negative y over the square root of 6 minus x squared minus y squared. And doesn't that imply that x is equal to y? Multiply both sides by that denominator, you get negative x equal to negative y, x equal to y. So if x equal to y, look at that constraint equation, x plus y minus 2 equal to 0. That is, x plus y is equal to 2. But since x is equal to y, we have x plus x is equal to 2. 2x is equal to 2. X is equal to 1. But that's also the value for y. Plug 1 comma 1 into the function. That's the square root of 6 minus 1 squared minus 1 squared. We get the square root of 4. We get 2. So we have a maximum at 1 comma 1 comma 2. Right? Yes, ma'am. Okay, okay. That's good. That's good. We talk about, India said that she got hers a different route that she took. We'll talk about different routes that you can take in chapter 15. That if the vector field is conservative, then it doesn't matter what route you take from A to B. All different routes still exert the same amount of energy. So it may take you a little bit a longer route, but you may travel a little bit faster compared to a shorter route, but you still end up at grandma's house. Okay. Which I think there's a movie coming out with the Big Bad Wolf or something like that. So All right. Let's see. Now let me work this one. This guy involves x, y, and z now. So use Lagrange multipliers to find the indicated extrema. Assume x, y, and z are positive. I'll work this one and then you work the next one. I won't work the next one. I'll just give you the answer. So I'm just going to go straight to it. I see that 2x is equal to lambda. 2y is equal to lambda. 2z is equal to lambda. Does everybody see where I'm getting at? Right? Okay, very good. So what that implies is that x is equal to lambda over 2, comma, y is equal to lambda over 2, comma, z is equal to lambda over 2. I replace these values for x, y, and z into that constraint equation, and so we get lambda over 2 plus lambda over 2 plus lambda over 2 is equal to 9. So we get 3 lambda over 2 is equal to 9. This implies that lambda is equal to 6. 4. 6. Yeah. Just want to see if y'all were awake. Yeah, right. You said you're not. Man, it's just rough getting up in the mornings. Jeez. This class should have been at 9 o'clock, you know? Oh, boy. So, if lambda is equal to 6, then x is equal to 6 over 2, and you get 3, and that same value for y and z. So we have a minimum at 3, 3, 3, comma 27. Okay. Any questions there? All right. You work that one, and then we'll be done with this section and chapter. Yes, I give it to you. Yep. You get x equal to y equal to z. Yep. Very good. So you get x equal to 1, y equal to 1, z equal to 1. Is everybody good with that? Yes, sir. It's not 4, it's still 3. Right, right. That like that previous problem where you get the function value, so you have like 4 coordinates. It's still 3 x, y, and z. Typically, if you have a fourth quadrant, a fourth term, it's typically a constant that's being derived from x, y, and z. So I mean that it could be heat flow, it could be pressure, or something that's not actually being calculated by the volume per se, but comes as a constraint from the volume. So yes, sir. Yep. So very good. So here you get x equal to y equal to z equal to 1. And so you have a max at 1, comma 1, comma 1, comma 1. And it's still in the third quadrant for x, y, and z. So, yes, sir. Very good. Any questions? Let me give you the sample exam.